All right, we're going to get started. Just a reminder, Lightning Talk submissions are still open. We've accepted the talks for this afternoon, but we still have slots for tomorrow. And if you have something to talk about that you can fit into 10 minutes, a new idea, something cool, something that can help people out, something you'd like input on, whatever that may be, Lightning Talks are a great slot to put that in. So you can submit those. You can just go to the main NANOG website and go to the meeting website and find a link from there, or you can go directly to pc.nanog.org from your browser and submit them through the NANOG Program Committee tool. Want to thank the social sponsors from last night, BTI and CoreSite. They did a fantastic job, so thanks, guys. Reminder on surveys, of course. Tell us how we can make this program better for you. We'll win an iPad mini. So we'll give away the first survey gift from yesterday, I believe, before the break. And then we'll have another one for today's surveys. So please, again, that's the best way to tell the program committee how we're doing and how we can serve you better. Again, those should be linked off of the meeting website at nanog.org. For our opening talk this morning, we have a man who I have a ton of respect for, Dave Meyer, who I saw this talk once before and was incredibly confused by it for the first 10 minutes, but then it made an absolute sense. And so anyone here who operates a network and thinks about how to balance complexity against simplicity should find a lot of truth in this. And so I'm really looking forward to Dave presenting this again. Thanks, Dave. Thank you.
See if I can operate this thing. Hey, good morning. It's great to be here. So this work is work that's been kind of in my head for the last 15 or so years. But I started working, as many of you know, I've been working in this, doing this complexity stuff for quite some time. Working in sort of the systems science area, systems biology, risk management and stuff. It's all kind of related. But what wound up happening was I started working on this SDN stuff because it kind of looked interesting a couple years back. And it sort of came together, two things kind of came together for me is, one, why was this SDN thing happening? And the second thing was, what did it really mean in terms of, the complexity profile of all of this stuff. So that's kind of what this talk's about. It's a little different than maybe what you'd expect at NANOG, but let's try it anyway. Okay, so I had this idea. I was working at Cisco, and I had this idea that there's these giant things that people aren't noticing, and so I just call these things macro trends. I'll just talk about a couple of them in a second, and how they led to this SDN thing, and then kind of tie that into the whole complexity and some other things that are related. And then what is the context? Like, why were people trying to do SDN in the first place? How do we get here? Where is it all going? And what's SDN? Well, what is this all about? And how does it affect us? So that's what I was trying to get at with all of this. So let's see. So this talk is supposed to, I thought this was so funny, and nobody ever gets this. I think it means I'm old or something. So this talk is supposed to be controversial and provocative, and there's a little bit of science. And I try to, I try to kind of ground this stuff because, as you guys know, the whole SDN stuff is pretty much hype, or most of it anyway. There's some reality in it, but so what am I trying to do here? So I'm trying to convince, or at least get you to think that there are some trends here that we can identify. And basically the effect of all of this is volatility and uncertainty, which is kind of bad news maybe. But this talk is going to talk a little bit about why that is, how SDN and software in general is causing or accelerating this effect. And then, finally, maybe what we could do to take advantage of it. And, by the way, I like to send these decks to Sean Duran. I don't know, anybody know Sean? Anybody remember Sean? Yeah, well, the Sprint guys probably do. Anyway, so I had to take advantage of this because I was thinking about this anti-fragility stuff, which I'll talk about in a bit. And Sean just said, forget that. Let's see if we can just survive it. So, that was his comment on this. Okay, so here's another. So these macro trends. So here's the thing: is that when I have a slide and I don't have a graphic for it, I generally just type it into Google Images and see what comes back. And this, happened to be, this is what came back when I said macro trends. This happens to be at a place called Piahe on Maui, but it's a pretty nice picture, and I kind of liked it, so I left it. So I have this slide. So here's a macro trend. Intelligence in everything we do is evolving at a great, rapid rate. And I showed this slide to people at Cisco and Brocade, for that matter. And of course, being an equipment hardware vendor, maybe this wasn't the greatest slide to show senior executives because it kind of is saying the future is all about software, where when people are in the business of building hardware, they kind of bristle at this a little bit. But the basic thing is if you look at nature, and one of the themes of all of this is that we try to look at a lot of systems that aren't just the internet, because the internet is just an instance of a system that we can characterize by various properties, and I'll talk about that in a second. But if we look in nature, which is one of the favorite places to look for complex systems because it's unbelievably complex, what we see is that over time, it basically became about code, right? Once you get a bunch of cores and stuff, everybody has a bunch of cores, and you want to start building more sophisticated functionality, it's always software, right? So in nature, what we saw was sort of reptilian brain, stuff that does your autonomic nervous system, stuff that forwards packets maybe. And what happened was intelligence evolved. What was the intelligence? Well, it had a good processor, but it was really about software. So there are these architectural features, and I've listed a few of them here on the left, and I'll talk about these in more detail as we get into this, but that you can identify in all of these systems, including the internet, and I'll explain where that is. But I want to talk about two of them in particular, those ones in red there, which are RYF complexity, which is a fundamental thing in these systems. I was talking to somebody about this last night. It's kind of a counterintuitive thing, but I'll give you some examples, and you'll be able to see where this has happened to you. And bow tie architectures. And the other ones are, things that we see every day, like very distributed systems, layered systems, and component reuse. Component reuse is one we're pretty good at, like traceroute, right? There's no traceroute's about reuse. So here's another trend. Another one that, my employers haven't liked over the years is that, you know how vendors like to sell end-to-end solutions. I think the trend is away from that. De-siloing is what I've been calling this. Sort of basically from vertical to horizontal integration. We're seeing this everywhere. Everything open. I guess exchange points too, but APIs, protocols, open source, all of that stuff. Everything modular, pluggable in these architectures. And so basically the future is about ecosystems here, right? And we see this both in nature and in other technology areas, and we're just getting to it now. We certainly see it in compute. Here's another one that the employers weren't all that happy about, which is sort of network-centric to IT-centric. So this is what like the Etsy network function virtualization stuff is all about. But it represents a shift in not only influence, purchasing influence and architectural influence, but speed. So, NetOps to DevOps is kind of the way I summarize it. There's other ones too. Everything virtualizes. Okay, we've seen this. Data centers, yeah, we've seen it. Integrated orchestration is something people are always talking about. So we've seen all these things happening. And the bottom line here is that, it's about software. It's integrated orchestration of almost everything, and some of this is not desirable because, if you get integrated, or perhaps not desirable, because if you get integrated orchestration of all this stuff and starting to be your identity and other things like that, there become privacy concerns and things like that. So it may not be quite as nice in some cases as it seems. But the bottom line here is increasing compute, storage, and network power, however you want to measure power. It really just comes down. It just means increasing volatility, really, and I'll explain why. So, this stuff was supposed to have something to do with complexity and SDN. So let me go there for a second. So, what was the problem space that people were? How many people have come up to you and said, well, what problem does SDN solve? And so I kind of tried to answer myself that question. I couldn't really figure it out. So I tried a couple of different things. And I went back and I looked at the stuff that came out of Stanford, which is sort of the incubator for all of this stuff. And basically what they were saying was this, with this thing in bold here, which is basically, how do we provide state-of-the-art network infrastructure and services while minimizing TCO? And that's kind of like, okay, yeah, everybody wants to do that. And so the hypothesis here, and this came from Nick McEwen and Scott Shanker and these type of people, was that it was the lack or the inability to innovate in the network, in the underlying network itself, coupled with the lack of, programmability, proper abstractions, things like that, that really caused this problem. And I kind of question whether or not that's true, so just hold that question. And again, here, again, the future's uncertain even with this. And how many people have heard this? Oh no, don't skate to where the puck is, skate to where the puck's going to be. That seems like I hear that all the time, right? And I thought about that, and I thought, hey, well, that's really cool. That means you know the curve, and you can just integrate along the curve. But here, you don't know the curve, and so that's kind of meaningless, right? So there's quite a bit of this stuff out there. And so, if you just buy the hypothesis for a second. So what's the problem? So okay, oops, can I go backwards? Yeah. So, thank you, Google Images. I think I typed complicated network or something like that into Google. I got this thing. But I mean, basically what I looked at it for a while and I thought, okay, well, there's some interesting things in this, right? One is that there's all kinds of different forwarding planes in our networks right now. Like there's firewalls, there's routers, there's switches, but they're not treated in any systematic way. There's no network level view, they're a bunch of boxes, right? And finally, the configuration of this and the policy are all intertwined. So what's the policy of your network? Well, it's an ACLs and things like that. Or in a lot of cases there are. But maybe it's this, protocol stacks. Now, working in the IETF over many, many years, one of the things that I've done, I'm guilty as anyone else, is we like to make protocols. That's what we do, right? So we built a bunch of protocols. And so you get protocol stacks that look like this, and they have, in your phone or wherever, you have a lot of different protocols, a lot of touch points, but few abstractions, open interfaces, or anything like that. So it's all a stack of things that are sort of almost unrelated. And the result is the network becomes robust because we put in a lot of complexity, basically, to create that, but at the same time, it becomes fragile. And this is where this complexity stuff starts intersecting with all this. So the network has become robust yet fragile. Now that sounds like a contradiction. Let's see if we can make some sense out of that. So this is kind of a famous curve. If you look at any of these large dynamic systems, what they are is that they're heavy-tailed curves. And basically, what this is saying is, like on the vertical axis, it's robustness, and usually that's parameterized by some feature, right? And then on the horizontal axis, there's complexity. And what it's basically saying is, if you look at, let's see, I hope I shaded this. Yeah, I wanted to shade the area under the curve, but I don't know PowerPoint well enough, so I gave up. But basically, if you look at where the curve is rising, or if you want convex, that's where things are becoming more robust with the addition of complexity. And if you look on the other side of that, where things are concave, then things start becoming fragile. And really, what this curve is saying is, you need complexity to achieve robustness, but there can be an upper bound on that, but there's no upper bound on how much complexity you can put in your network. And I'm sure all of you have seen that. So if you get on the right side of this, P max number, you're looking for a new job. So basically, as you move to the right here, you have increasing numbers of policies, protocols, configuration, and their interaction, and code, right? I mean, I was talking about software and its effect, but it itself is uncertain and volatile. I mean, like your router would never crash. That wouldn't happen. Line card wouldn't crash. Wouldn't have a bug. This never happens. So it's volatile, inherently. So I start looking at this, and I've been looking at this stuff for a while, but I wanted to kind of cross it with this software revolution or evolution that we're seeing. And so first off, let's see if we can get a definition of robustness and fragility. So something's robust if it's invariant to some kind of set of perturbations or events that happen. In other words, it's invariant, it doesn't change, right? Fragility is kind of the opposite. Although it's a second order effect. I'll talk about that a little more. But what's really interesting here, and this is sort of the network, the system science, the biological systems people, and the risk engineering people have kind of come together. And the risk engineering guys work on the fragility side quite a bit more. They try to do things like build stress tests for banks in the EU and things like that, and to detect this kind of fragility. But it's all the same stuff. So what it comes down to is a system can have a property a system can be robust to some set of things that happen, but at the same time be fragile to other things. And in fact, maybe the same things, in fact. And so these are trade-offs that happen, and these are kind of hard limits. These systems actually, is this a property of these systems that this trade-off will exist. So I gave one example here, which is, if you try to build high efficiency optimization, you basically create, unreliability perhaps, or hard to evolve systems. In other words, optimization causes things to be brittle, right? And we know that. So it's kind of a hard limit in these systems. And another, I was talking to somebody else about this the other day, and they were going, well, how about in the network? And I can remember this one time when we were first building the campus network where I worked. And, the idea was, okay, well, we'll put a subnet in every building. That's kind of intuitive. And we'll put a router interface in every building. And that's all really cool. But what happened was, all of a sudden the thing was fragile to the loss of the router interface. So we wanted to put another router interface in it to give it some redundancy, right? Okay, but we didn't want hosts to have to carry routing or know about this. So, okay, HSRP, VRRP. But then, so we created robustness to the failure of the one interface, but in the process of doing that, we created fragility to bugs in the HSRP implementation, MAC address assignment, all of this stuff. So what you saw there was you created robustness to one thing, but it uncovered or created a fragility somewhere else. This is a general property of all these systems. So here's some examples from nature and other places. So if you build in a human or in a mammal efficient and flexible metabolism, that's robust, but we see it go wrong. The same mechanism creates obesity and diabetes. Complex development, what's fragile is microbe systems, right? They have complex development so they can grow, but they're also fragile. Immune systems, well, we've all seen this, anti-inflammatory or inflammatory and autoimmune disease. Regeneration or no, it's extremely robust in mammals and humans, but unfortunately, it can go wrong, right? So you can create robustness and fragility at the same time. We have complex societies; they're very robust, but we have epidemics, we have war, things like that. And advanced technology is, of course, nothing ever goes wrong there. I've never seen anything go wrong there anyway. So it turns out, this is what's really fantastic, it turns out that these evolved mechanisms for robustness allow for, they even facilitate these novel severe fragilities somewhere else in the same system. And, this is really odd. It often involves hijacking and exploiting the same mechanism. So we've never seen that, like DDoS, amplification attacks, all these things. Same thing. So there's an underlying systems theory that explains a lot of the behavior that we see as engineers. And again, as I said earlier, this trade-off space is a hard constraint in these systems. If you create robustness, you will create fragility somewhere else. And that was the first thing I saw that said, well, maybe there's a design paradigm that we can deduce from this, because really, at the end of the day, all of this it's interesting, and we learn a lot, but we want to be able to build more robust and better networks, scalable, evolvable, all of these sort of things. So if you want to kind of think about what robustness really is in a network, you can think of it kind of like this. So scalability is a kind of robustness. It's robustness to changes in the size and complexity of a system as a whole. We want to build scalable networks, obviously. Evolvability is a kind of robustness. It's robustness to lineages, to changes on long time scales. We want to build scalable and evolvable networks. The internet is a good example of this. You can look at these other things too. You know, reliability is robustness to component failure, efficiency to resource scarceness, modularity. So this is a very general thing. And we think of these as engineering quantities, but we don't have a framework to stick them in yet. And that's what a lot of this is trying to do. So in our case, you know, protocols, systems, operations all fit this. And we see this stuff all the time. Okay, so a friend of mine told me that when you're given a talk like this, for every equation you put in the thing, you lose 50%. So don't use more than one equation because, you know, pretty quickly that decays, right? And, you know, people are looking at their laptops. That's what I do anyway. So, but the fragility thing has really been expanded by people in a totally different domain, which is sort of quantitative risk management. These are the guys who are the quants, or the people who are the quants, right? The people who build these spectacularly complex models for hedge funds and things like that. So here's a bit of a formal description, and this is actually a crazy thing because I'd studied this for a long time, and then these guys from this other field came in with this definition of fragility that fits so well. But the basic idea here is you have some event, I just call it Z, and you have some function that maps this event and a property onto what's called a harm function, right? And it's negative value. Excuse me. So that's why. I mean, you could flip the sign around and change the inequality. That doesn't really matter. But the idea here is that the effect of one big event is nonlinear, and the small event, so basically on the left side of this thing it says, okay, I have something that's of size n times z, that's a lot worse than n times the smaller one. And I'll give some examples of that so you can understand, because that's a really fantastic property. And our networks have that, by the way. So if you take the coffee cup, right, and you go, you know, you do this like maybe 1,000 times or whatever, it's like if you add up the total distance that the thing has traveled, it'll be 10 feet or 15 feet. But if I drop it once, and it's fine, right? It's no problem. But if I drop it once from 15 feet, it gets destroyed. This is not linearly related. And that's the important property. And as I said, when I said earlier that fragility is a second order effect, that's because it's actually the acceleration of harm that's important here. So that's it's kind of really a fantastic thing. And in fact, nature requires this, right? So if you walk around, you lift your feet up, you know, 5 centimeters every time you walk. If you jump off something like 10 meters high, you're going to die, right? But if you walk around, we're all okay, or for the most part. And so it's required that there's this nonlinear relationship, otherwise we'd all be dead. You know, this is kind of a new way of looking at the fragility piece of the RYF stuff. Let's see, what else do I have in here? Oh yeah, this is the other thing. It's related to scaling. Now, how many times have you guys, somebody said, oh, that scales like n squared? How many times you said that? Because we say it a lot, because we have adjacencies, and so we have n choose 2 things to look at, and that's n squared. Well, what that really means is that the harm function, if you want to look at it this way, really has this constant acceleration. It gets bad with constant acceleration, 2, because 2 is the second derivative of n squared, when things get weird enough, you know, when they get big or weird. And so you might think it's theoretical, but it's really not. You know, ARP storms, congestion collapse, AS7007, DDoS, you know, it all causes this nonlinear damage. So this gives us a framework to kind of understand how these events affect us. Okay. Let me just say one thing about anti-fragility. This is one of the things I was telling somebody earlier. This is one of the things that's really captured many people's imagination. It's kind of a new idea. Robustness and fragility are the opposite of one another. Anti-fragility is something different. An anti-fragile system improves as the result of stress. So what's an example of this? Your skeletal and muscular systems. If you don't have gravity and the stress of gravity, your bones will just deteriorate. They require stress, right? But this is found in all kinds of systems, economies, forest ecosystems, internets, things like that. So if you want to get some metaphors for this, if something's fragile, what happens? Like, you know, you send something in the mail, you go, it's fragile, what can happen to it? Well, it can, in the best case, it can arrive at its destination undamaged. In the worst case, it gets completely destroyed. That's what fragile is. So upper bound, it's okay. Lower bound, complete destroyed, right? What if something's robust? If something's robust, it just survives the mail. It doesn't get damaged. It won't get damaged, and it'll get there as, undamaged. But if something's anti-fragile, the lower bound is it's robust, but the upper bound is it actually gets better. So it'd be like if I sent something, this doesn't happen obviously, but it'd be like if I sent something in the mail and it got all beat up, but when the process of it getting beat up made it better. Now, is this abstract? Not really. Jim Cowie just wrote an excellent blog on peering and the Syrian internet crisis that went on there and explained how it was anti-fragile. So what happened? There was stress to the system, governmental control of key access points, not enough diversity in peering, all of that stuff. What happens? Internet engineers build ways around this, and the network becomes more complex but more robust. So the internet itself is anti-fragile. That's an interesting idea. Something to think about when you're building things. So what it all comes down to, at the end of the day, I like this definition for complexity, is basically so the internet's a highly organized system. It's not random. It's not a bunch of random stuff. It's highly organized. So when we talk about complexity in organized systems, it's about that structure itself. And it basically arises from design properties that all of us build to create optimizations or to create robustness to uncertainty in the environments, in their components. So what do? The HSRP thing, or what do? You have diverse peering, things like that. So this might also be obvious, but a network's a really general thing. It turns up in nature all the time. It's a graph, right? And so many of the things that we see are networks. So these things are common in a lot of ways. So we think of the internet as sort of this artifact that we built, but actually it has a lot in common with things like I'm mentioning here, like energy metabolism, like transportation systems, even the main sequence in stellar evolution. And I remember when my kids were small, I used to tell them, we're at Costco and we're standing in line, I used to tell them, everything's either a network or a queue. See, everything you can see is almost explainable that way. So, and that's true. So it comes as probably not a lot of surprise that even as network people, we're network people, a lot of this stuff comes from studying other systems that give us clues as to how we can build more reliable and more robust networks, so biological systems, things like that. So all that's cool. All right, that's nice. But what does it mean for us where, us means, operators, engineers, architects, and how can the effect of this really change the way we build and operate networks? So keep that in mind because we'll come back to that. What I've been, I'll just take an aside here. One of the things I've been trying to do over the years is sort of bridge this gap between the guys who are doing the science, because it gets pretty difficult. The people who are doing the science, it gets pretty difficult, and you have to have some serious physics chops to do some of this stuff. And it gets away from the lay people like us pretty quickly. But there's some really good intuition we can get from it. And so these architectural takeaways are things that came from other domains but are directly applicable to the internet space. So in this work that people have been doing in a diverse set of domains, it turns out that there are fundamental architectural building blocks that are found in these systems that are both scalable and evolvable. And of course, that's what we want, right? RYF complexity, I talked a little bit about that. It's kind of a counterintuitive thing, but it's core to these things. Bowtie architectures, I'll talk about that in a second. Massively distributed with robust control, TCP, BGP. And let's see what else. Oh, highly layered. We have that. But we also have layer violations. That's also a characteristic. So these things have layers. All of these systems are layered, but they have layer violations. TCP IP, layer violation. I don't know what Warren was talking about one at breakfast this morning. I forgot what it was. Somebody said, oh, that's a layer violation. Or maybe it was Rudiger, I'm not sure. Layer violations are an inherent part of these systems, even though we'd rather have that. They have protocols. Well, yeah. And there's a property called degeneracy. I'll come back to that if we have time. It's something like redundancy, but more general. and it aids in evolvability of these systems. Okay, so here's bow ties. This is an idea that came from systems biology. I love systems biology. It's very cool. But anyways, this idea came up from a guy, I think I have the cite to the paper there. But the idea was there's constraints that deconstrain. So here's the idea. So you can see how this is a bow tie and there's a knot. This is the metaphor these guys used, right? And you can see that on the left side of this, on the input side of this, what's there? Well, it's just a bunch of chemical phenomenon going on. But in the middle, there's a highly specialized, rigid, kind of basically information processing unit is what it is. And then on the right side, you build everything on top of that. Now, why is that a constraint that deconstrains? Because on the right side of it, well, let's start on the left side. On the left side, it can take any input. So it's unconstrained on the left side. On the right side, you can build anything you want, including all of life. So the example I have here is, I don't know how many people have biology in their background, but there's a molecule called ATP, adenosine triphosphate, which every cell on the planet uses for energy metabolism. So once you know you're going to have that, you can build all of life on top of that. So that's how life, that's one of the bow ties in biology. Okay, so that's really interesting. But how's that related to what we're doing? Well, anything look familiar? So this thing on the right is the internet hourglass. How many people have seen that? Okay. So this explains, for example, why the internet is adaptable the way it is, but it also explains why certain things are rigid. Explains why it's hard to deploy IPv6. Why? Because IPv6 is in the knot, or in the narrow waist is what we call it in the internet space, but it's in the knot, right? It also explains why it's hard to deploy IPsec, same reason, right? But this is a feature of any scalable system. It'll have, so the bow tie is sort of like if you view things as horizontally layered, and we look at it as vertically layered, but it's the same phenomenon. So now, if a system doesn't have that, you gotta ask, what does that mean, right? And we'll get to that. So back to, so this had something to do with SDN and complexity. So how did we even get here? So again, the idea was everything that was networking was just too vertically integrated, just too tightly coupled, non-standard, no interfaces, anything. And it kind of goes without saying that these folks who were cooking this stuff up in the early days were saying, hey, we can't do our work, we can't do research because we can't see inside any of this stuff. Okay, that's all really cool, and that's probably true. But does that have anything to do with running a production network? Hold that question. I'm not sure. I don't know. But if you take this SDN thesis and put it a different way, the idea was, okay, well, we want to do what happened in the compute industry, right? So virtualization layer, all of this kind of stuff. And the idea was, oh, well, it's this, right? And this is a standard, SDN picture, right? And so the question is this. Is this a good analogy, really? And I'll tell you, the thing on the right is characterized by complete separation of control and data. Is that a good idea? Just ask the question. Open interfaces to the forwarding plane. I don't know if that's okay. And kind of centralized control. And I'll talk about this in a second, logically centralized, right? So if you take a closer look, this was the Nick McEwen picture. This is really what it is, right? So there's a controller, piece of software, it's a piece of middleware. There's some applications, routing, whatever. And then there's this open interface, open flow, and a bunch of switches, right? That's the real picture, right, if you drill down a little bit. Now, I was talking to James Hamilton about this, and I was saying, the whole analogy thing is kind of bothering me. So he handed me this slide, right? And he said, well, this is really what's going on. Basically, the architecture, so if you look at this changes the architecture of the network and the devices in it. If you look at this, really what happened here was there was a standard, kind of a standard instruction set, x86, and then everything opened up. So now I have Linux, now I have everything open. That's really what it was about, everything open. It didn't really change the architecture. So it doesn't look to me like that analogy is very good. And in fact, again, this is another one of these things that my employers don't like, but this is what I really think is a better analogy is if you had a really robust open source network OS and protocol stack and you ran that on, and you had it on a white box of some sort, that would be more like I got Linux on my favorite x86. Anyway, So I'm questioning that as a underlying thesis. Oh yeah, and I mentioned this thing is logically centralized, right? So we know, one of the things we know from our experience and from system science, like I was describing, is that for scalability and robustness and resilience, you need distributed systems, right? So really, the central controller can't be centralized. That means it's a distributed system, right? So these guys came up with this word called logically centralized, which means distributed. Why we need new words for that, I'm not really sure. But once you have a distributed system, you have inherent trade-offs in scalability and control plane convergence that are just basically fundamental stuff from distributed systems. I don't know if people know what the CAP theorem is, but it explains what these trade-offs are. And there's another thing here, right? Now you've broken if you do this, you break the fate sharing between the control and data plane. And so that puts a lower bound on how fast the control plane can actually converge. There's actually physics involved here, right? I mean, basically you have to detect it. So there has to be a packet that goes between the controller and the switch, or the switch and the controller. So you got the RTT there. And then you have to process that packet on each side. So you have packet processing time plus this RTT, and you might have to do it along a whole path, because remember, the OpenFlow SDN model sets up what are essentially soft PVCs, right? So there's paths that are set up that you have to do. So you can ask yourself, what are the implications of this with respect to resilience and convergence? This is another one. There's really nothing new here. This has been tried many, many times. It works in circuit switching sometimes. It hasn't really, as far as I know, worked too well in packet networking. I don't know how many times flow-based forwarding has been tried in the internet space. Many times. So let's just go on a brief aside on what OpenFlow is, because I wanted to tell people a little bit about what this is with a little bit more of a critical or skeptical eye towards it, because every time I've heard people talk about it, it's usually a sales job, and I wanted to think about it a little more. So here was the original switch model. I'm not sure where this picture came from. I couldn't find where I got it from, but basically this was the sort of what OpenFlow 1.0 was. So if you think about it, it was just a TCAM. So a packet would come to the thing. If there's a matching rule, it would do whatever the TCAM, whatever the match action table told it to do, like the ACL table on your router, and it would forward it, right? If not, if it got a miss, what it could do is it could redirect the packet to the controller, in which case it would set up a path if it had that, and then send the packet back to the head end, or it could drop the packet. So basically what it was there's a switch model, which is this match action table stuff I just described. There's a wire protocol, some kind of way of communicating this, and then you had to transport over TCP or SSL or something like that. So what was going on with this? Well, first off, it was it's intuitively nice, but it's too simple, because there's not feature functionality gaps. And then it wasn't expressive enough. The language itself actually precluded you from doing a lot of things that you might think are obvious. For example, learning and forwarding bridge, or URPF and longest prefix match at the same time. So, all right, that was a problem. So this is the next model. This is OpenFlow 1.1 and beyond. So it's multi-table, and it's sort of similar. The packet comes to the thing, to the switch. If there's a match, in this case what it does is it just collects the actions instead of executing them immediately until the end of the pipeline, and then it executes them. And the reason for that is because every table wants to see the original packet, so you can't actually modify it. You can do it actually, but if you do modify it in flight, it's pretty non-deterministic what's going to happen. So is this why do this, right? First off, why do this? It's because there's a combinatorial explosion of routes versus policies, and TCAMs are typically not that big. In fact, TCAM's the hottest, least efficient part of the forwarding path, and so building a whole switch on that is kind of, I don't know. So, but I kind of looked at this a little more, and I thought, well, okay, that's cool, but what really can I know? Well, I tried to compute the complexity of just finding a path in this thing, because I thought for sure people have done this, but no. So it's at least n factorial, right? Because the first table, you have n ways of choosing it. The second way, you have n minus 1, blah, blah, blah. So it's n factorial paths in this. But it's worse, because the constants in there are gigantic. But, okay, so maybe you can conquer that. But again, it's too complex and too brittle. As I said, the algorithmic complexity is just too high. What's a flow in this? Nobody can even describe what a flow is. It's not naturally implementable on ASIC hardware for the reasons I mentioned, and there's a lot of other reasons. There's a bunch of problems with the abstraction itself, and there's architectural questions, which, that's a whole nother talk we could do. And I'll tell you that in the ONF, there's a group called a working group called Forwarding Abstractions, whose main goal is try to constrain things so this is actually implementable on something. Obviously it's implementable in software, but in hardware. So again, the question I have for all of you guys to think about is the flow-based abstraction the right thing for general network programmability? Maybe, maybe not. So now here's my perhaps controversial view. So OpenFlow and SDN are a design point in sort of a larger space of things. And people like to, divide this up in different ways, but it's not the only one. The larger space has things like control plane programmability. I don't know how many people are following the IETF, but this is things like I2RS, BGPLS, Alto, so forth. And there's overlays, VMware Nicira. And then there's compute storage and network programmability. And I think everybody will be glad to hear that there's something called software-defined storage now too, whatever that might be. So that's another one. But I have this other model that I'm calling a continuum, right? And this is, by the way, I can't really draw in PowerPoint. I don't have the patience for it, so this is kind of the best thing I could make. But so if you look on the left, you have this thing that I'm calling forwarding SDN, and it's characterized by all the things I was mentioning for OpenFlow. Separation of control and data, logically centralized control, open interface to the forwarding plane, and these are things like OpenFlow SDN. Forces could fall in here if you know forces. In the middle, there's some control plane SDN. I'm calling it control plane SDN, and this has the property that you maintain the existing distributed control plane, but you make it programmable. That's I2RS and all of those things, netconf, etc. And then you can go sort of to the other side of it, where you have overlay, what I'm calling overlay SDN. So what's overlay SDN? This is where you don't really care that much about the underlying control plane or forwarding plane, as long as you have, 32, 64, 128 by, ECMP or something like that, and you just put another control plane on top of it. So, there's a highly dimensional space in here of things that can be done. So back to all of this, just to try to tie this up a little bit. If I look at this, and I'm just using this one of those features I was saying, because you want to kind of look for these kind of things and say, well, do these things have these properties or not? So if you look at this control plane SDN, this doesn't really affect the architecture of the network. It just gives you more programmability of the existing control plane. The overlay SDN thing is just an application to the IP layer. The IP layer doesn't really know about it. Now, OpenFlow SDN, I don't really know where that fits. I don't even know if it has this structure. I couldn't really nail that down. I tried for a while, but I couldn't see it exactly. So I'm not sure about that. So if it doesn't have this property, what does it say about the scalability? That's a question, right? Oh yeah, and of course you have software, right? So again, this is if you combine open loop control, software, and Moore's law, you get randomness, uncertainty, and volatility. Trust me. So where's it all going? Yeah. So I typed that into Google Images, and I got this thing of Zweiberg drowning in garbage. I'm not saying we're drowning in garbage. I just like the picture. More seriously, I think the high order bit here is something like, because of all this volatility that's coming basically from software, that everything's going to be pretty much cloudy for a while, or maybe permanently. I think a good thing for us is that we work in the narrow waist part of the thing, so we're in the most stable piece of it. But if you're above that, things are going to get interesting. And I just give an example here of, I got to look at my time. I give an example here of something like Spot Cloud. It's a spot market for compute, right? And Amazon has one too. And what happens here is you can just buy a VM anywhere on the planet and spin it up. You could put a routed network on top of that, and you could build another cloud on top of it. So once you have the ability to do that, the idea that you would understand, deeply what your traffic matrix looked like on any kind of time granularity, well, we've seen what happens there. I would say that conventional technology curves are going to hang around. We just heard yesterday the nice talk about optical. We know we're going to get 400 and 1.6 and all of that, or more core density, all of that stuff. And that sort of corresponds to the reptilian brain piece of it. Somebody's going to have to forward packets eventually. I mentioned this stuff about ecosystems. I can't make that point strongly enough, and open everything. But okay, so just to wrap this up, what do we do about all this stuff? Well, so my sense of it is that we really need to protect the architectural features of the network that have made it scale and made it operable. So things like the narrow waist, we're pretty good at that. I mean, we did IPv6. That's been troublesome, but we're getting there with that. But we're pretty good at that. We don't change the IP layer a lot, and we're pretty good at component reuse. Traceroute, as I mentioned earlier, and a lot of other component reuse. That's a good thing. And I mentioned this. I'm not going to say this again, but just expect a lot of volatility coming from the top. The bottom's not so much, right, because it's hardware in general, unless it's vSwitch or something, and it moves slower. But above, it's software, and it can move at any rate. DevOps, I mean, I think we all got to get in the groove. I know that several nanogs ago, VJ was talking about the kind of people he was wanting to hire, and I think it was before the term DevOps actually was even, coined. This is another property, is that, like, in the internet space, we develop our understanding kind of bottom up. That's an important thing to maintain. And, design, I mean, my sense of it is that we really need to expect and understand where we're designing robustness and fragility and build things that will help us evolve. We don't really go, a lot of times we don't think, we have extension headers, we have things like that, but a lot of times we don't think about evolvability. And there are properties that we could talk about that allow that. So that's kind of the summary of all of this stuff. So I think I'm done. Yes. Do I have time to get a question from anyone? Oh, good.
Hey, Todd Underwood, Google. So thanks for the talk, Dave. I love it. I think one of the things that there's a set of network architectural principles going on the sort of most mundane part of the talk, because the other part's probably too hard for me to understand. So I'm just focusing on the concrete parts that I could follow. So when you look at the general,
I made most of it up.
Yeah, that was no. So when you look at, like, you're assigning specific architectural or implementation strategies to robustness or to fragility, that seemed pretty unmotivated and pretty unjustified. So in particular, it's not clear to me that massively distributed systems are not themselves pretty fragile. We spend a lot of time on cascading failures, and cascading failures are enormously difficult to mitigate in distributed systems. So that's one point. So the other point is just a niggling point, but like convergence times on separated control plane and forwarding plane, you talk about the round trip time between the controller and the forwarding nodes. Like, what about the multi-hop round trip time between forwarding planes finding out about remote failures, which is convergence takes a long time in distributed routing protocols.
Yeah.
Obviously.
So let me take the second one first. Okay. So what we do is we use eventual consistency so that we don't have to do that, right? Actually, I didn't have time to talk about this, but CAP theorem basically says, you can have consistency, meaning the state's consistent everywhere. You can have availability, or you can have partition tolerance, CAP, C-A-P. But it's choose any two. Yep. And so what we did in the internet space, and we didn't take advantage really of the deep knowledge of the distributed systems community, is that we built something called eventual consistency, so we didn't have to do that. And yeah, if you had to have strong consistency constraints, then the problems that you were just describing would arise, but we don't. So we tolerate things like microloops and transient black holes and things like that, and the trade-off is the convergence time, right?
Sure, I'm just saying, the second point sort of niggling, I'm just saying that the consequence of and the distribution of those outages are just as bad in distributed routing protocols as they are when you have a semi-centralized control plane.
Yeah, I don't disagree. I mean,
trading off a different kind of latency and a different kind of uncertainty.
Yeah, and this RYF thing is about just those trade-offs.
But go back to cascading failures and tell me how to fix that, because I got some problems with that.
Okay, we'll do that later.
Damn.
Dinesh.
Hey, Dave. A couple of things. First, nice talk. Second, your title says CTO and Chief Scientist at Brocade. You sure you're not at Cumulus Networks?
Well, I'm here. I'm at Nanog right now.
But your point also raises the hourglass principle to me also raises the point, two things. The trouble that it seems to me that networking faces today, especially in the data center space, is the mainframe business model, the violation of the end-to-end principle. The networking vendors, in their attempt to make it vertically integrated, are saying the network is the centerpiece of the world and everything has to be subsumed in there. And in the process of that, we have complicated the central piece so much that people either innovate around it or find ways to break this opaque blob in the middle. And the SDN is an attempt to try both.
Yeah.
And I think the way you put it, I like the way you put it, the central piece, the reptilian brain, so to speak, the hardware, with its well-known protocols such as BGP, which have been tested, we know how it works, is a good way to do all the forwarding. So the hourglass principle is maintained, and virtualization overlays the SDN, the ability to manipulate things from the edge of the network, maintains the end-to-end principle and the hourglass point that you have. Mm-hmm. So thank you.
Thanks.
This will be the last question. Go ahead.
Randy Bush, IJ.
Hey, Randy.
Two things. Sadly, due to CGNs and NATs, the waste of the hourglass has moved up a few layers.
Yeah, it's controversial. I admit that.
It's not a good thing. But the fear of a distributed algorithms is, I think, a CircuitZilla problem. The telcos just don't believe in datagrams and they don't believe in distributed algorithms. And yes, you have to be a little more formal and a little smarter to do it well. Somehow we've survived on them for a long time. Complexity is, and fragility are not caused by any particular technical factor. They're caused by the fact that a bunch of funny monkeys are doing this stuff. And the funny monkeys do Parkinson's real well. And we push distributed algorithms to the point where we get annoyed at their ugliness. And if we centralize things, all that does is give us time windows for a couple years before we complicate that far enough that it's going to be screwed. Right? Centralizing it is not a panacea for our complexity disease. But what it does do is decouple the control plane from the data plane. And I think we've learned time and again in this industry that having two layers that relate to each other that are non-congruent are always really fun, just uglier than hell.
Thank you. Thanks.
Thanks, Dave.